In this lecture, we're going to continue our discussion of first order differential equations, and we will expand our discussion to include some additional definitions. So the first thing to look at is what is a linear equation and what is its general form. So often you will see um, some equation that kind of looks like this, where a1 and a2 are functions of x. Y is a function of x, and that's equal to some other function of x. And of course, what you're trying to solve for here is y. So this is referred to as a linear equation. And remember, these functions of x, they can be nonlinear, which can't have nonlinearity in or terms of y. So this could be e to the x, it could be cosine of x, it could be really any function of x. So often you will see the differential equation, especially when you're doing models that are based in engineering or physics. You'll see the differential equation written in this form. And so the first thing to do is to determine, is this a homogeneous or an inhomogeneous equation? If it is a homogeneous equation, then this g of x is equal to 0. Now, in physics and engineering, what this represents, what a homogeneous differential equation represents, is it represents what we call the natural response of a system. So let's suppose you have a spring on a mass, and you come in and you do a one-time display, or a mass on a spring. You do a one-time displacement of the little weight that's hanging by a spring, and you let it go, and you kind of know intuitively what's going to happen. It's going to go up and down, up and down, up and down, and eventually friction by air and friction in the spring is going to slow it down, and so it'll oscillate with smaller and smaller amplitude until basically the oscillations die away to, for all practical purposes, 0. So if just left on its own devices after a perturbation, that's what happens in the mass on the spring problem. Um, so that would be considered the mathematics, the differential equation, and the mathematical expression that describes that would be considered the natural response, because you're giving it some initial perturbation and then you're letting it just kind of evolve on its own. So the natural response is a function of the elements that are in the problem. So for example, it would be a function of the spring constant and other physical parameters that are a part of the system. The inhomogeneous differential equation has that differential equation equal to another function. In this case, your author has referred to it as g of x. Now, g of x can be considered a forcing function. So to continue with our analogy of the mass on a spring, let's suppose we suspend the mass on the spring from a platform that can move. And so now we're going to repeat the experiment. We're going to displace the mass on the spring. But now let's say we have a moving platform that's oscillating with some frequency. So what you're going to see in the behavior of the mass is you're going to see a combination of the natural response, which is how the mass on the spring would behave if you had no moving platform, and the forced or driven response, which is the fact that the platform from which it is suspended is also moving. So in mathematics, the natural response is represented by the homogeneous equation. The forced response is represented by the non-homogeneous or inhomogeneous part, and the solution is almost always is always a combination of the natural response plus this forced or driven response. So the first thing to do so that's just a little physical insight onto what these things mean. So the first thing to do is to take your first order differential equation and divide everything by this coefficient a1 of x, which can be a constant, can be a function, could be 1. So you divide through by that and you put the equation in standard form. So standard form always has the first derivative of x with no coefficient, the y function with some functional coefficient p of x, and then equal to f of x if the equation was inhomogeneous. So the standard form of the equation has the property that its solution is the sum of a homogeneous solution and what we refer to as a particular solution of the inhomogeneous or non-homogeneous equation y of p. The homogeneous equation is separable, and so this allows us to solve for y of c, the solution to the homogeneous part of the equation. And then we can use a technique called variation of parameters to solve for the non-homogeneous equation for y of p. Now, in fact, there are some other methods to solve for y of p that are a little bit easier and more straightforward for most differential equations and most functional forms. And so we'll look at that as well. But in this textbook, he does talk a bit about variation of parameters. All right, so first let's look a little bit more at this idea that we have two solutions, a homogeneous solution and a particular solution. Sometimes the solution of the homogeneous equation is referred to as the general solution. So we would have a general solution, y sub c, and a particular solution, y sub p, and the overall solution will be the sum of those two, y sub c plus y sub p. So if we take yc plus yp and we plug it in for y, then we get the following, and then we can separate out the 2 points, yc and yp. And so what you really find is, that you have two separate but similar equations, one in y of c and one in y of p. And so this first part is equal to 0 because we've defined it as the homogeneous part. So by definition, it's going to be equal to 0. And then the second part is equal to f of x. So it's kind of just expanding, making it look more complicated, but actually to prove a point that what we're going to do actually is we're going to solve these separately. So the homogeneous equation looks like this, and we can separate it. So it's separable in x and y. And so what's shown here is the homogeneous part after we have done separation of variables, and it looks like this. And then what we can do is we can integrate. So if you take this p of x dx over to the right-hand side of the equation, solve for y, integrate both parts, and what you'll get is first you'll get a natural log, and then you'll raise everything to the power e. And so the solution for this is that the general solution is some constant c times e to the negative, e to the negative integral of p of x dx. So now if we just write y sub c as some constant times y1, then we can write y1 as e to the minus integral of p of x dx. And then that basically gives us a fairly straightforward solution for the homogeneous part of the differential equation. So next, we're gonna look at the particular solution. So the particular solution, we can use a procedure known as the variation of parameters. And so basically we're trying to find a function u so that the particular solution is equal to this u of x times y1 of x. And then that's going to be, when we solve it, given that we've already solved for y1, that's going to be u of x e to the minus integral of p of x dx. So we're assuming that the solution for y of p is the same as the solution, as the general solution, except that c is replaced by some variable parameter u. So when you substitute y of p is equal to u y1 into the differential equation, so let me just point out the general rule for a solution of differential equations is that you are making an educated guess at a solution, which is what we've done here. We've made an assumption that our particular part of the solution has this u of x part, and then you plug that into the differential equation, and if it is a solution, then you can force conditions where that is true. So the first thing to do is to substitute that into the differential equation, and that initial term in the differential equation, dy dx, since y is a product of two functions of x, these first two terms consist of using the product rule. And then the next term is where you have your p of x u y1, and then you have f of x, and f of x is some defined function. Well, now we can basically look for terms in u here and here and collect those, and when we do, we find that what we have here is the differential equation for the for the homogeneous part, and we know that that's 0, so that's going to go away. So this whole term here, because y1 was the solution for the homogeneous equation, and this is our general form for the differential equation, you can go back a couple of slides and see that we've already said this is equal to 0. So independent of what u is, this entire term goes away, meaning we're left with y1 du dx is equal to f of x. So what we want to do there is we now want to separate the variables. So we will move y1, which is a function of x only, we'll move dx over to the f of x side, and we're left with du. So we have this expression right here. Then we integrate both sides, and so we get u is the integral of this expression. Now remember, we've already defined y1 of x, and so 1 over y1 of x is this integral e to the integral of p of x dx. So we can substitute that in and do a little bit of algebraic manipulation. And so what we end up with is this expression right here for the particular solution. And so now if we look at the total solution, we have the solution to the homogeneous part and the solution to the inhomogeneous part, and they're added together. So we go back and grab our solution to the homogeneous part, we find our solution to the inhomogeneous part, we express those as one general solution. Now, this can be simplified, okay? You notice we have this e to the minus integral p of x dx term, and it shows up here and here. So if we take this entire equation and we multiply it through by e to the plus integral of p of x dx, so this is what we're going to do right here, then we end up with this expression, which is a much simpler expression. And now we take its derivative, and you can see that once you take its derivative, you get the following expression. If you now divide the entire thing by e to the integral of p of x dx, you basically have equation number 2. So this e to the integral of p of x dx is referred to as an integrating factor. It will show back up in a future session. Now, at this time, I'm going to end this video because that is a lot of theoretical information, and we will go to a video that looks at a couple of examples of applying this. So we'll end the slideshow now and go to another video.